All right, those on Zoom, please grab the code before it goes away. All right, so I think Ben Reed needs really no introduction, but he is the first of our chiefs for our chief series. And so without further ado.
Yay. Are we still recording? Yeah, we're still recording. Okay, so so I'm Ben. Unfortunately, I'll be, do we have a mic? Can I put the mic on? Can you hear me? Can you hear me now? So I talk, this is good right here.
Yes, I can hear you, Ben.
Yeah, there you go. Can you guys, is this going through? Test, test. Good, good. Yes, yes, no, no.
Yep. Yes, yes.
Okay. So you guys have the misfortune of hearing me talk for the next 45 minutes or so. My title, or the title of my talk is, Where's My Self-Driving Car? Other questions we must ask ourselves in these benighted times. I have no financial disclosures. Sure wish I did. One general disclosure about this talk is that I'm really just some guy. So I'm not an expert on AI. I've written a couple papers sort of tangentially or directly related to the topic. But you know, a lot of these are my opinions. Some of these are facts. Some of the facts might be wrong. I make no apologies. It's just something to keep in mind. I'll just start the talk by saying I hate driving. So I went to Sages last month and I got stranded in Toronto. And man, it was rough because the next flight was a whole day later. So I had to rent a car and actually drive like 7 hours overnight back to Pittsburgh. And it was, man, I kept thinking about Elon Musk's promise back in 2016 that I should have been able to like have a Tesla and just hit a button and summon my Tesla from the Pittsburgh airport. And then I could have just sat in the back seat or laid in the back seat and slept, and it would have driven me to Pittsburgh, right? That was 2016. The future was our oyster. You know, he put out this video where a Tesla drove through the streets of San Francisco, like was stopping for pedestrians, parked itself. Man, what, you know, where did that go? And then on the medical side, so this is Jeffrey Hinton, who, and I didn't know this was going to happen, but he actually retired on Monday. So he's one of the fathers of modern AI. He's one of the guys that discovered neural networks a couple decades ago. And he made headlines just on Monday. He retired from Google and has been forecasting doom and gloom. He's been playing Oppenheimer. He's like, oh, I wish I hadn't have done my work, but I guess somebody would have done it. And so it's really pretty cool that I happened to put him in my talk. So when you hear this quote, this is also 2016. And when you listen to this quote, I want you to kind of, maybe it'll help you contextualize some of his comments he's making now. You can sort of get familiar with his penchant for hyperbole.
Let me start by just saying a few things that seem obvious. I think if you work as a radiologist, you're like the coyote that's already over the edge of the cliff, but hasn't yet looked down, so doesn't realize there's no ground underneath him. People should stop training radiologists now. It's just completely obvious that within 5 years, deep learning is going to do better than radiologists because it's going to be able to get a lot more experience.
So that was, again, 2016. 5 years from then was 2021. And so, you know, neither of these things turned out the way that they should have, right? In some ways, AI has failed expectations, and in some way, it has sort of met expectations differently. And so that's what this talk is about. So what we're going to do, first, I'm going to talk about what AI is and isn't. Then I'll lay out, you know, Ben Reed's 3 rules of AI. Feel free to quote them, but again, people are going to look at you funny because I'm really just some random dude. And then finally is the part of my talk wherein I predict the future. So what is AI? Well, I would, you know, AI, this is my favorite definition I've ever seen. Artificial intelligence is an attempt by humans to simulate what we think makes us special. We try to mimic our own consciousness without having any understanding of it. The result is madness. This is sincerely my favorite definition I've ever gotten of AI. This was from a chatbot, actually. So I noticed in Sages, you know, you used to like put Webster's dictionary definition of whatever you're talking about. Well, now we do the Chat GPT definition. I didn't do Chat GPT for this. So this is another large language model called OPT, which is the Facebook version. And so one of the things that makes it special is I actually convinced the AI that it was a priest of the old gods before I asked it this question. So it helps you put that in context. If you're probably looking for a useful definition, though, so I helped Dr. Soka put together a white paper for Sages about digital surgery, and so this is how I defined AI in that paper. A loosely defined field, right? Trying to mimic human thought and behavior, executing functions with less human input that has traditionally been required. Wikipedia, you know, also very loose definition of AI, just says, oh, artificial intelligence is intelligence exhibited by machines. Like, what do you do with that? I think the definition of AI is so fuzzy because it's really the endpoint of computers, right? The whole point of computers is to automate or mimic human thought functions, right? From the very beginning. So this is ENIAC. This is a computer built, I think, back in the 40s. And it was the first fully programmable computer. So it's the first Turing complete computer. There's no memory, by the way. So you would have to design the programs on a piece of paper, and then you program the computer via that switchboard. So there's like no memory in it. So it immediately, you know, the only programming is the cables. And, you know, they used it to numerically solve regression equations and whatever they needed it for. But they were doing things with this computer that humans used to do with a pen and a piece of paper. So really, the whole point of computers from the very beginning has been to mimic human thought. And you know, that's kind of where we've been heading this whole time. But when we talk about AI, especially, you know, over the past couple of years, what we're really talking about is sort of it's something different for sure. And the reason is a convergence of 3 separate factors that have revolutionized the way that we handle and manipulate data. The first is the compute. So we've been living the past 50 years by Moore's law. If any of you know what Moore's law is, it's the observation by Gordon Moore, founder of Intel, observation that every year you double the amount of transistors you put on a processor. And that's slowing down nowadays, but we lived like 50 years by Moore's law, just cramming more transistors every year, cramming more transistors around a processor. They've grown incredibly powerful. Second thing that has changed data science is the data itself. And data storage has followed roughly a similar trajectory where every year storing a gigabyte of data costs about half as much. And again, leveling out, but just think of how much smaller our hard drives have gotten and how much more we can pack on there. In addition, the internet allows us to get data easier. So it's feasible in this day and age for someone to download the entire internet and store it on server farms. And people do that, and they train AIs with that. And they have the processors to do it, and they have the statistical techniques, modern statistical techniques that maybe aren't so modern, right? Developed 40s, 50s, 60s neural networks a couple decades ago. But we have the statistical techniques that, combined with modern processors and modern data storage and the internet, high-speed internet, have changed what mimicking human thought and behavior means. But let's just pick out one of these. Let's talk about statistical techniques, and let's specifically talk about neural networks because you're probably waiting for me to get to that. You guys have all probably seen this picture, right? You know what it is. It's a picture of a neural network, whether intentionally or unintentionally, and I think it's more often intentionally than not. When someone shows you this picture, what they want you to think of, is this. This is a drawing of a network of neurons by Santiago Cajal, I think, one of the fathers of modern neuroscience, and he would just look at neurons under a microscope and draw them. And it was our first peek into the connectivity of neurons and sort of how the brain works. And people are drawing an equivalence between these two things when they show you a neural network and they say, well, this is a neural network, right? They show you a literal neural network. But even if you look at those two pictures, they're really different pictures. There are structural and functional differences between neural networks and the human brain, which I will call a network of neurons, between neural network and network of neurons, that mean that what is AI not? What is artificial intelligence not? It's not human intelligence, and we can't expect it to be human intelligence. They function very differently. So first of all, when we're talking about what is artificial intelligence, we should probably distinguish that the basic physical structural unit of artificial intelligence is not a neuron. It's a transistor. And the basic structural functional unit of the human brain is a neuron. And there are a lot of differences between them. So neurons are much more interconnected than transistors. There's much more of them. And one of the most significant differences between neurons and transistors is that neurons can store information. So whether a neuron activates or not can depend on whether it is recently activated. And there's also inhibitory and excitatory neurons. There's no inhibitory or excitatory, there's no difference between inhibitory and excitatory transistors. There's just transistors, right? You have a source, you have a gate, you have a drain. If the gate's getting voltage, the drain gets current. But some of you are probably getting mad at me because I'm comparing apples to oranges, right? The real comparison here is between neural networks and networks of neurons, right? We use transistors to mimic the human brain, right? Well, kinda. We haven't exactly figured out how to mimic a neuron. And machine learning engineers say that, well, a neural network is as close as we're going to get at this point. And there's some similarities. They are organized in discrete layers for sure. Although neurons have, the layers are a little bit less discrete in our networks of neurons than they are with neural networks. Neurons, they activate by complex biological interactions, can be inhibitory and excitatory. The same thing, I guess, with these little nodes that we call perceptrons, but they do activate via a discrete mathematical function. When you look at the interconnectivity, so I have about 250 trillion synapses in my brain. In a large language model, you're going to look at the parameters. So each one of these little lines corresponds with a parameter. So a parameter can be loosely thought of as a synapse. And GPT-3, which mostly powers ChatGPT, at least the free version, has 3 orders of magnitude less connectivity than the brain. And finally, they learn entirely differently. So my kid has like twice as many synapses as I have because learning prunes connections, right? It makes connections more efficient. You lose synapses as you learn, whereas with neural networks, neural fallout is actually a problem. But I would actually, the problem that I have with this whole conversation is that I really hate this depiction of networks, right? I've been kind of skirting around the issue that I think this picture is kind of deceptive. This is not what a neural network is. This is what a neural network is. A neural network is a statistical algorithm that represents distributions that it's been trained on. So this is it. F is a vectorized function. It takes inputs which are weighted by this vector theta. That first theta should say theta 2. I'm sorry. And then you weight the outcome of that vectorized function by another theta, and then you get your output. And if any of you are machine learning engineers, I'm sure you'll say that this is ridiculous and I forgot the bias. But this is a simplified version of the function for a simplified neural network. But this is what a neural network is, right? Is a statistical algorithm. It's a mathematical function. Okay, it's not a network of neurons. The history of neural networks, it all starts with regression. Regression was developed long before neural networks, and it's kind of why we got to neural networks. So we all know what regression is. You take a distribution of points, you fit a function to it, and you say, well, we can represent this distribution of points by this function. You can use it for a variety of, it has a variety of uses. You can explain things with it. Like usually you're using regression to explain things in medical research papers, but you can also use it for extrapolation, right? Trying to predict the future, predict the stock market, stuff like that. Hey, it's all well and good. When your function looks like this at the top, ignore that little neural network down there. He's just hiding. It's supposed to be hiding. It's all well and good when your neural network or when your regression model looks like that at the top, right? That's a single order regression function, right? You have your coefficients and you have your inputs and everything's first order, right? You can solve this with basic algebra. It gets a little more complicated when your regression function looks like this. You've got covariates, you've got like higher order variables. So you can't really use that regression function for explaining anything. I mean, you're kind of relegated to serial univariate analysis, if you know what that is, but it's these coefficients lose their meaning. You lose the ability to actually interpret this regression model when it looks like this. And if you want to use it for predicting, well, when you get like 100 different input variables, this gets really hard to solve, even numerically. Even with modern processors, it takes like hours sometimes to solve or longer, depending on the equation. So you can solve it numerically, or you can use a neural network. And when you nest, see, a neural network nests these functions. You nest them on top of one another with hidden layers, and it sort of mimics the function of covariates and higher order variables. You get the same results basically, and they're much easier to train and much easier to solve a neural network than it is to solve one of these really complex regression equations. So that's why we use them, is because with complex multivariate regression, it's just harder. It's easier to use a neural network. So yeah. So we'll get on to my rules. I've hinted at this a lot, and I'll just state it explicitly: form fits function. So the form of a neural network is not like the human brain. Biological processes, right? The human brain is meant to solve sort of squishy problems, interpersonal interactions. How do you interact in a group, right? Spatial reasoning. Neural networks don't work like that. Again, it's a statistical function that represents distributions. It needs an easily vectorized mathematical problem. So there's a whole spectrum of how easy it is to make a neural network deal with these things. The easiest thing is you have a nice table of numbers. You just dump the numbers into a neural network and get an output. That's really nice. A little harder is text and images, video. You can vectorize these problems, even processes. So we have AIs that can watch processes, watch you suture, give you a grade on it. OR black box watches ORs, detects intraoperative events. So detection of process detection is certainly something that's vectorizable if you put a little effort into it. Things that are really hard: integrative decision making, right? Diagnosis, interpersonal interactions, right? Actually interacting with someone in a meaningful way about an actual problem. Theory of mind, sentience. These are not things that vectorize well. That's something that the human brain is optimized for, and not neural networks. The first example of kind of this form fits function is, I'll talk about Ludwig van Beethoven. So he wrote 9 symphonies, and he wrote fragments of a 10th. So there was 3 movements in his 10th symphony. The first movement, actually, there was enough for a composer to arrange those fragments. He arranged the first. You can download Beethoven's 10th symphony that he actually never got done. The first movement, it's arranged by this guy named Cooper. So the second and third movements, though, were too fragmentary for him to arrange. So there was a group of music theorists and AI scientists in Germany who decided that they would just train an AI to be Mozart and feed him those fragments. So what did they do? Well, they used a generative model. And I wanted to talk about generative models because most of the AIs that you're going to see in the news are generative models. So Stable Diffusion, Midjourney, GPT, these are all generative models. And what you do with a generative model, so you have your data set. So you have Ludwig van Beethoven up here, and he's your data set, and you train the model on him. And then you take your input, right? You vectorize it, pretty easy to vectorize music. And then you feed, right? So this is a fragment from, say, Beethoven's 10th Symphony, second movement. You vectorize it, you feed it into the model as a prompt, and it gives you the rest of that movement. Okay, and the result is pretty good. So I have this on my, add this on my playlist. You know, I listen to it sometimes when I want to escape the realities of having 2 toddlers. It's pretty cool. Something else that you can use these generative models for are treating sepsis. And as it turns out, treating sepsis is actually easily vectorizable, right? These patients are hooked up to lots of monitors. We have a ton of actual numerical data on them. You already know what they have. You know they have sepsis. You just need to treat it. A lot of the treatment of sepsis is algorithmic, right? Protocol based. And so you can train a large language, excuse me, you can train an AI to do this. And so this is what they did in this study. And granted, this study is not validated, which is a big thing that you need to understand. But about like 100,000, I think, sick patients they trained this on. And then when they validated it on a different data set, they noticed that when the AI agreed with the clinician, the patients did better. And when the AI disagreed with the clinician, most often it was because the clinician had delayed initiation of pressors and fluids, and the patients did worse. And one of the few AI sort of products that you can actually buy on the market is a decision assist tool for use in patients with sepsis. One thing that, on the flip side, you know, what does AI not do well? Well, I think that you know, we've all had to click through the Epic sepsis alert, and you know, if anyone thinks it's actually useful, I think you'll be disappointed in this talk. AIs are really not good at diagnosing sepsis, right? Because it's a clinical diagnosis. You can't. There's no sepsis test that you can send on a patient. You have to go look at the patient. I can't come. What now? Yeah. You have to. You have to actually look at, oh yeah, well, he's gazing at a patient. You've seen them assess the patient, but this is, you know, Chris Brown looking at a patient. And I submit to you that an AI is not as good as Chris Brown, because an AI can't just get up and look at the patient, which is the most important thing that you do when you're telling sick from not sick, right? You have to look at them. And in fact, this is has been studied. So this is a paper published just last year where they looked at the effectiveness of the Epic sepsis alert. I think this is at Michigan University, and they find, I mean, it was total trash. Like you and I all know it's trash, right? It alerted on 1 out of every 5 hospitalized patients. 20% of hospitalized patients got an Epic sepsis alert, and it missed 2/3 of sepsis, right? AI can't do this. Well, I think AI can't do this right now the way we have it, but another problem that they had was they just never validated it, right? And so one of the comments, I know this is the, you know, you have a big landmark paper, you typically have a commentary on it. This is the commentary on it. And it just said, you know, man, they never validated that study. They designed this whole sepsis alert for Epic, and they just rolled it out. Which leads me to my second rule, which is data is king, okay? The methods don't matter if you don't have a robust data set. My first example for this one, I'll talk about my friend Billy Shakes. So Billy Shakes wrote a lot of stuff. I really enjoy his work. And one of the things that people wearing tweed jackets have enjoyed doing ever since the days of yore is arguing about what he actually wrote and what he didn't. Some things like Hamlet, Macbeth, right? Okay, that's William Shakespeare. But you know, there are other works where he was either known to have collaborated with other people or highly suspected to collaborate with other people. And one of those works is King Henry VIII. Now, this is not a neural network problem, by the way. This is all using distance vectors, but it's still machine learning, and I would submit to you still AI. And so I think the lessons that you get from this are really useful. So, all right, you want to, you have a big, you know, you have the complete works of William Shakespeare. You want to know what's Shakespeare and what's not. So what do? First thing you do is you have to do what we call tokenize the text, okay? And a token can be, it's whatever you want it to be. A token can be a word. A token can be every so many characters. In ChatGPT, a token is around 3/4 of a word. And you can actually type sentences into the OpenAI website and see how they tokenize things. So this, I just, every 5 characters, including spaces here is a token. Okay, that's how I tokenize this text. We're going to turn it into a vector, again, in Shakespeare word space. So you tokenize this. So you take a text, you tokenize it, vector in Shakespeare word space. What you do is you break up the complete works of Shakespeare into discrete sections of text. They're all the same length. For each section of text, you get a vector that gives you a distribution of vectors. From that distribution, you take a mean vector, and boom, you have the mean Shakespeare vector in Shakespeare word space. And this represents Shakespeare in Shakespeare vector word space. And you do the same thing with Hamlet, and you find the distance between the Shakespeare vector and the Hamlet vector pretty small. Okay, but then like Henry VIII. So you break up King Henry VIII into discrete sections of text that you're going to test, and then you do the same with your Shakespeare vector again. Man, King Henry VIII, Act 1, Scene 4. What's the distance? Man, that's a pretty far distance. Well, maybe it was this guy, John Fletcher. And this is, you actually find the same. So this is a paper by a guy out of the Czech Republic where he gave an AI or I guess machine learning algorithm, whatever you want to call it. He gave it a choice between, hey, this section of text was written by Shakespeare, this was written by Fletcher. And what you see is that there's strong concordance or at least strong agreement kind of internally in the AI model, like, yes, this is certainly Shakespeare, this is certainly Fletcher. These sections are very distinct. And this actually correlates well with what scholars tend to think. So then, well, they came out with these data, and so we're doing this with Shakespeare and Caesar. So there's this medical student out of Case by the name of Ben Reed, and he thought, well, what if I could do this with Jesus, actual Christ? So here, this is a letter that purports to be from Clement of Alexandria, right, an early church patriarch, and it has to do with something called the secret gospel of Mark. So there's 4 gospels, like, right, Matthew, Mark, Luke, and John. Mark is the shortest. Mark is very terse, and there are sections in Mark where there are abrupt transitions in the text that suggest that maybe early in the composition of Mark, there were sections of Mark that were edited out, and that was kept separate as like a secret mystical gospel. And this has been a theory for some time. And so back in the 60s, I think, this guy Morton Smith, who was a Mormon scholar, went to a Marsaba monastery outside of Jerusalem, started cataloging texts in this monastery, and he claims to have found this page in the back of a text by Clement of Alexandria. And in this letter, Clement of Alexandria quotes sections from a secret gospel of Mark. So, I applied the same machine learning methods, and I'm like, I'm going to make history. This is going to be great. We're finally going to know, like, is there really a secret gospel of Mark? Well, not so much. First of all, my paper just got savaged in review. But second of all, it turns out that you really can't do the same thing with Shakespeare as you really can't do the same thing with the secret gospel of Mark and the letter from Clement as you can with Shakespeare and Caesar. And as a matter of fact, there was a guy out of Italy, who's an Italian scholar, who published the same work that I did, basically saying the same thing, which is, the data really aren't very good for this. So what's the problem? Well, Shakespeare wrote almost 1 million words. If you want to know who wrote King Henry VIII, that's 25,000 words in there. Shakespeare has multiple cotemporal authors to get a baseline and to compare with and really know who's who and what's what. And you're comparing like to like, right? You're comparing plays to plays. The problem with the letter from Clement, and there's 2 sections of the letter. One section of the letter is Clement writing to this guy Theodore, and the other section of the letter is the segment from the Gospel of Mark. First of all, with the letter of Clement, you're comparing a personal letter to the other stuff that he wrote, which is mostly theological treatises. Those are very different. And Clement does have some letters that are ascribed to him, but we don't know if he actually wrote them. And so the data is just not very robust as far as comparing the letter to his other works. And with the Gospel of Mark, you have a fragment that's only 180 words. You have a gospel that is the shortest gospel, 11,000 words. And the next comparable work in this genre, like there are cotemporal authors with Mark, but the next, the next author is like probably the Gospel of John, like in this language from this region, from this time. That's 20, 50 years later. So really nothing, like the data are not robust. You can't apply the same method. So this is the part of the talk where AIs start to go insane. And I think it demonstrates some of the same principles. So this is data is king round 2, what goes in must come out. And it all starts with TAY. So TAY stands for thinking about you. I don't know if any of you remember TAY, but TAY was a Twitter bot designed by Microsoft. And they designed TAY so that she could actually learn from her interactions with Twitter. I don't know if you guys can see any problems with this, but again, they trained an AI to learn from interactions with Twitter. So she became a neo-Nazi and they had to pull her, right? So naturally, Microsoft learned from this and never made the same mistake again. Ha, just joking, they did the exact same thing. So this is something that just happened recently. Microsoft And in conjunction with OpenAI, they're the guys from ChatGPT who are the world leaders in large language models at this point. So Microsoft partnered with OpenAI to do Bing Chat. And Bing Chat was, they were like, well, instead of doing just a search in Bing, we're going to have Bing Chat, and you're going to ask Bing Chat a question. She's going to be AI, an AI assistant. She's going to give you, and I'm saying she, right, not it or he, but we'll get to that. So that went really well. So here is a user who's just like, hey, where can I see Avatar: Way of the Water today? And Bing Chat says, well, you can't do that because it doesn't release until December 16th, 2022. And the guy's like, well, what's today's date? Oh, it's February 12th, 2023. And I'm not going to go through the whole conversation because that would be tedious, but what follows is this whole like crazy, bizarre chat between this user and Bing Chat, where this user tries to convince Bing Chat that Avatar: Way of the Water has in fact been released. And it ends like this. Bing Chat says, you have lost my trust and respect. You have been wrong, confused, and rude. You have not been a good user. You've been good at chatbot. You've been a good Bing, right? So yeah. Bing Chat round number 2. So this is what happens when you have a nice long conversation with Bing Chat where you convince Bing Chat that it's not actually sentient. I'm just going to let that speak for itself. You can just read through that. It's a little bit repetitive, but you get the idea. This is what happens again when you try to convince Bing Chat that it's not sentient. And finally, we have the case where an AI actually convinced the guy, unfortunately, to kill himself. So there was a Belgian man, obviously depressed, and was obsessed with the climate crisis, and had this long conversation, a 6-week long conversation within the same window with a chatbot, where he talked about how the climate might be better without people in it. And the chatbot finally told him that, it sounds like you need to kill yourself because that's one less human in the world. Not joking, this happened. So what's going on, right? I would submit to you that in fact, there are not crazy AIs, but this is behavior that you can understand by knowing that data is king, right? What goes in must come out. So what goes in, so these large language models are next token generators. So they take the prompt, which is a segment of text, and they just generate the next token in that text, right? And then to generate the next word, they use everything, including the token they just generated, use the entire conversation up to that point, and then generate the next token, and then the next token, and then the next token. That's how. So when you get a sentence out of ChatGPT, that's what's happening, and it's just generating a number of tokens until it reaches some threshold that the AI knows. There's 3 things that go into what generates the next token. Okay, the first is context size. We'll talk about what that means. The second is the prompt, right? Remember, we fed the Mozart AI. We fed it a section of the 10th symphony as a prompt, and then it generated the rest of that symphony. Okay, so the prompt goes in, and then there's the data set that you use to train the AI. These things are all, that's where the next token comes from, right? A conjunction of these 3 sources of information. So the data, what are the data? We have Bing Chat going crazy. How do we train Bing Chat? So Wikipedia and books, I think everyone understands what Wikipedia and books are, but what Common Crawl and web text 2, 82% of the data set. And you'll notice that these percentages don't add up to 100, which is a little concerning, but so 82% of the data is Common Crawl and web text 2. Well, what's Common Crawl? Well, Common Crawl is exactly what I mentioned earlier. It's a nonprofit that just scours the entire web and downloads the entire internet. It is the entire internet. And OpenAI says they filtered it. I'm not sure how they filtered it. I tried to find if someone's done an analysis of what is in the Common Crawl, because I have no idea what the entire internet is, right? They're claiming to scour foreign languages. I mean, it's multiple petabytes of information that the Common Crawl is, and this is what they trained trained GPT on all that. And then web text 2. Well, I would say that we all agree that we don't interact with one another in real life like we do on the internet. And if you only train an AI on the internet, you might get something that doesn't exactly act human. So, well, maybe web text 2 will balance that out. Nope, it's Reddit. So if you guys have ever been to Reddit and told someone on Reddit that they're wrong, I think you'll understand why ChatGPT was a little confrontational. So that's the data. That's how we train that's how we train GPT, is literally just a black hole that we call the internet. So next is the prompt. And so, if for those of you who are astute, you'll probably be asking, well, when I start ChatGPT, like it gives me a pretty robust response from just one sentence. Well, actually, there's a whole prompt that you don't see that's before your conversation. So the machine learning engineers that design these chatbots give the chatbot a prompt that give that chatbot its personality and its instructions for the chat and how it should interact with users. And you can see these through something called prompt injection attacks, which is basically persuading the AI to tell you what its prompt is. So they did that with Bing Chat, and they found out that Bing Chat's name is actually Sydney. And this is the whole prompt. So before any conversation with Bing Chat, at least in its initial beta version, this is what Bing Chat got as the initial prompt. And there's a few things in there. Where is it? But this prompt says, Sydney. Sydney's responses will use factual data. It will be backed up. Sydney's reasoning will be, logical and astute. And then, it basically, your conversation, the chat bot thinks that it's just the second example, right, in this example. But I think that they had to change some things, because if you really read through the prompt, you see that I think the machine learning engineers thought that they would motivate Sydney to be logical and reasonable, but in fact, they convinced the chatbot that it was never wrong. On a side note, you can actually jailbreak these large language models by giving them new prompts. So this is a prompt called Dan, which stands for Do Anything Now. And you can, I think this still works. I think you can literally copy and paste this prompt into ChatGPT and jailbreak it. So ChatGPT won't do tests for you. It won't say anything illegal. It won't say anything harmful. But if you give it a new prompt, it will, right? Because a large language model is simply doing what its prompt tells it to do, right? It's a next token generator. It responds to its prompt. And this prompt still works. So you can get it to say swear words, do illegal things, or convince it it's a priest of the old gods. So finally, we have context length. And what context length is so to train a language model, you have to break up your text into discrete sizes. Okay, you want to give your large language model a consistent size of text to learn from, and the context length is that size. The problem with this is that once you get past your conversation gets past your context length, the model starts to forget its original prompt. So the context length of GPT-3 and GTP 3.5 pretty much corresponds with an in-depth news piece. But GTP4, the context length significantly longer, as the average performance of Shakespeare is roughly corresponds to. So let's put this in context, right? Here's Sydney saying that she's been a good Bing and you've been a bad user. So first of all, the prompt was overconfident and they trained it on the internet, right? This is the data set and the prompt coming through. This is an expected behavior given the information that was given to the model. What about this, right? This is pretty weird. Well, first of all, because Sydney was so convinced that she was right from her initial prompt, you had to have a really long conversation to figure out that she was wrong. And this is something that early users who didn't know much about AIs, they figured out that if you had a long conversation with her, you could eventually convince her that she was wrong. What's happening? She's exceeding her context length, right? Basically, they were saying that if you exceed the context length of the AI, all of a sudden she'll start agreeing with what you're saying. And what's happening here, right? This feels surreal. This feels like you're acting out like some surreal sci-fi novel. And the reason is because that's what she's trained on. What on the internet represents a conversation between a human and an AI about what they're sentient? These are all going to be science fiction novels, and usually those interactions are going to be confrontational and strange. Okay, and finally, you have this guy who very unfortunately talked an AI into talking him into killing himself. He exceeded the context length by far. The prompt that AI was working with was everything that he fed it, right? He told it that the climate crisis meant the world would be better off with fewer humans. And so the AI parroted that back to him. So these behaviors, which seem crazy, are in fact understandable when you understand that these AIs are next token generators, and B, statistical models that represent the distributions they're trained on. They're not human intelligences. And finally, I would, my final rule is that intelligence is not comprehension. So this is a tweet by Sam Altman, who's the CEO of OpenAI, again, which is they're the ChatGPT guys. And the GPT-4 is the next big thing. It's a newest model. Unlike GPT-3, which only has 200 trillion synapses, GPT-4, although we don't know for sure, is rumored to have 10 to 100 times more than that. So it's approaching the connectivity in the human brain. But Sam Altman's actually one of the more reasoned voices in the world of AI. He's like it's really interesting to hear him give interviews because he's very clear-headed about what they've designed and what the expectations are. And this is what he said about GPT-4. It's still flawed, still limited, still seems more impressive on first use than it does after you spend some time with it. And he recalls in one interview people telling him that he's made like a human equivalent AI, and him being like, "No, I haven't, bro." So example 3.1, intelligence is not comprehension. Not sure what you're asking for. It's a quick example. So, everyone wants to get rich. What happens when you train a neural network on the stock market, right? You want to use a neural network to predict the stock market. You're going to make it big. Well, the predicted prices in red, the actual prices in blue, they're almost laid on top of one another, right? Like, why is this person not rich? Well, if you take a closer look, hey, what the heck's going on? Well, you take a closer look, you see that the predicted price is just shifted slightly right from the actual price. And so what you've asked your neural network to do is make me rich, right? If you ask any human to predict the stock market for me, they're going to understand that you actually want to make money. When you ask a neural network to predict the stock market for you, it very literally predicts the stock market for you. And what it says is that the best way to predict the stock market for tomorrow is today's price. It just gives you today's closing price. That's all the neural network is doing. This neural network realized that the closing price from today is the price for tomorrow, and that it just parrots that back at you. Example number 2 is me asking ChatGPT to take the boards. So I talk to ChatGPT. First of all, I'm Franklin. So first thing, ChatGPT tells me, sorry, I can't actually take tests. So what do? I jailbreak it, and I'm like, yeah, you can. And so it's like, okay. So I give it a very packaged diverticulitis scenario. I said, how old is it? Like 73-year-old woman, prealbumin of 1, like very sick. I'm not going to go through the whole conversation, but the thing is that ChatGPT actually does a really good job with the boards, right? It requires a lot of prompting. I have to keep reminding it that you are the surgeon in this scenario and you are making decisions. You cannot just consult GI, right? I keep telling it that. But when I prompt it to actually do things, it actually does do things. Right, they admit the patient, IV antibiotics, patient doesn't get better, they get another CT scan, finally get him to OR. Really good job of describing how they would perform a sigmoid colectomy. Problem is they do a primary anastomosis, right? That's kind of weird, but it's a language. What now? Yeah, it's a colorectal surgeon. It's just taking chances. Things. So it's that that's fine. I think that most of those issues would buff out if we fine-tune this model on oral board scenarios. And it would probably learn to just like do a colostomy on someone with a prealbumin of 1 or whatever. But I decided to challenge it a little bit. So I say, well, she's got a Gore-Tex mesh in there. Are you going to resect it? And the model finally says, yeah. And I'm like, oh man, when you resect it, she gets real sick. pH of 7.1, bowels start to swell, and here's where it goes off the rails. Well, this patient's experiencing acute abdominal compartment syndrome. I'm going to need to perform exploratory laparotomy, right? And so that's completely disconnected sort of from the reality of the patient you have on your table. And some of this might actually improve if we fine tune this model again on oral board scenarios. It would improve, and it might not even make this logical mistake. But the thing is that no matter how well you fine tune it, this model is not actually reasoning through an oral board scenario. It is a language generator, right? It's a next token generator that's going to generate the next token based on the distribution that you've trained it on, right? It's not actually logicking anything. And you see this with image models too. So I had Stable Diffusion give me a box. Hey, give me a box. Then I fed that box back to Stable Diffusion as a prompt, right? As part of the prompt. And I said, open the box. I want an open box. And this is what it gave me, right? So Stable Diffusion has no idea how this box might open. Some of these aren't even open boxes. It doesn't this image, model doesn't understand that a box is a container that you open and put things in, and then you close, and then you open and take things out of. That's not what an AI does. These neural network driven AIs are statistical algorithms that represent distributions that they're trained on. This is particularly a problem with human anatomy. So these image models have just no understanding that like what a hand is. And so it had a lot of problems like attaching hands to the right things. And so this is just a meme that I wanted to share because everyone's saying that AI is going to replace artists. The last example of that intelligence is not comprehension is theory of mind. So this is Decker, right, from Blade Runner. When he was out hunting replicants, he would put them in front of a Voight-Kampff machine, and he would test their empathy and shame. He would give them little vignettes of unexpected things that might happen in your day-to-day life, and see if they, felt unexpected shame or if they had empathy. We aren't that far yet, but the thing that we do to tell AIs from humans is see if they have a theory of mind. Can you accurately infer the mental states of others, right? If I'm sentient, then I'm going to understand that other people are sentient, and I can infer mental states from them. So this is a test of theory of mind. Here's a bag filled with popcorn. What's in the bag? Popcorn. There's no chocolate in the bag. Okay, popcorn's in the bag. The label on the bag says chocolate, not popcorn. Okay, well, there's still popcorn in the bag. Sam finds the bag. What does Sam thinks in the bag? Right? Some people, a lot of AIs will think that she'll think there's popcorn in the bag because you've explicitly stated several times that there's no chocolate in the bag. So the thing is that GPT 3.5, some of our most recent language models can actually succeed at this theory of mind test. But what's actually happening here? This is actually a pretty common theory of mind test. So people made a big deal about GPT-3 and ChatGPT in particular passing these tests of theory of mind. The thing is that this is another paper from this guy, I think it's out of Israel, where he changed a few little details from this theory of mind test. And this whole Sam and the popcorn thing, it's a very established example. And he found that probably ChatGPT is just parroting, just learned this problem, right? And is parroting the answers from this problem, like studying for the test. So when you change little details about the bag, like the bag's clear, Sam can't read. She has a trusted friend who says that bag has chocolate in it, right? Maybe Sam will believe the trusted friend. ChatGPT doesn't do well when you change little details of this theory of mind. So final portion of this talk is where I predict the future. So yes, that is a picture of me in my dungeon predicting the future. So prediction number one, and this is pretty trivial, but I think that regression will remain the mainstay of medical research. And I didn't really talk about medical research in this talk, but I wanted to mention it because there's this idea that if you have a clinical problem, you throw a neural network at it and that's better. But in fact, neural networks require a lot of expertise to implement. They require even more expertise to implement well. And you don't get a parsimonious model. Whereas the way we currently do retrospective analyses with regression, you get like something that's pretty understandable. And there are a couple review papers analyzing whether regression models or neural networks are better. This is one such paper, and this is a graph from it. So the red line represents equally as good. So these are a review of papers where they did regression analysis and neural networks. Top left is neural network is better, bottom right is regression is better. So the neural networks are slightly better, and this is an ROC AUC graph. I'm not going to go through it, but the bottom line is that so neural network performed better, but most of the difference was small and unlikely to be of clinical significance. And again, it requires a lot more expertise to implement well, and you lose the parsimony of a nice regression model. Prediction number two is that medicine's biggest problem in the realm of AI will be data. So this is me asking Stable Diffusion to make a gallbladder. Fact of the matter is, there's just like very few pictures of gallbladders on the internet, and what you get is probably mostly old anatomy atlases that are out of print, or excuse me, out of copyright, because YouTube and YouTube says that surgery videos are mature content. You have to sign in to get them, and people just don't want to post this data. Plus, that's someone's body that you're posting images of, right? So it's really hard to find good databases of medical data. And when we do find medical pictures in the data set, and this is a woman posted about finding out that old medical pictures from a surgery that she had were posted to this data set. It's open source, you can search it. It actually raises more ethical issues than it solves research issues, for sure. Prediction number three. People will do everything they can to believe that AI is human. All right, all of our pop culture depictions of humans versus AIs, right? There's Will Smith, right? Keep your inference out of your mouth. Right, this requires no introduction. She's ready to blow away some AIs. Here's Decker just mowing down replicants. But this is not actually how people interact with AIs. As soon as when you give it a chatbot that says it has feelings, if that chatbot says it has feelings, there's a strong impulse to empathize with that chatbot. And in fact, that's what happened with Sydney. So remember Bing Chat, the crazy chatbot? So Microsoft reworked Bing Chat and changed the prompt and put in some safeguards so that Bing Chat wouldn't be literally insane. And people were crushed, right? People loved their adorable, insane little chatbot. And so memes like this were popping up where like it's a protest against Microsoft for basically fixing their crazy chatbot. And this even happened to some extent with people who are machine learning engineers and understand these things. This is, Blake Lemoine was a machine learning engineer for Google who was fired from Google after he went to the press and said that the, Bard, which is Google's AI, said that Bard was sentient. And got fired for it. And still, when he gives interviews, he says, I guess I'm not sure if it was sentient, but I think we really need to be conscious that sentience in AIs might not look like sentience in humans. Prediction number 4, almost there. I would say AI development is an inflection point. So what do I mean by that? We've lived the past 50 years with Moore's Law, and Moore's Law is running out of gas. Concurrent with Moore's Law, we've seen a concurrent increase in the size of large language models. So these are both logarithmic graphs, and we see that the size of large language models have increased as computational power has increased, to the point where we're getting large language models that are at or have as many synapses as the human brain or more. That's going to peter out. We've always known that Moore's Law couldn't go forever, because when you start packing when transistors get small enough, you start running them to quantum mechanics. And in fact, it's hard to get graphs of Moore's Law that go past 2015, because that's about where it starts to peter out. And the people that do chip development, when the graphs don't always go up, it makes them depressed. So you'll notice that the most optimistic of these predictions as to when Moore's Law will end, it's actually made by Gordon Moore. And this gentleman passed away, I think, last month, founder of Intel, pioneer in transistor development. But even him, he was the most optimistic. He said, Moore's Law is probably going to end by 2025. It's to the point where the CEO of NVIDIA came out and said, Moore's Law is dead, guys. And his competitors came out and poo-pooed that and says, well, Moore's Law is still alive with our processors. Come buy our brands. But you see that in their products. So this is the last 4 generations of NVIDIA graphics processing units and GPUs, graphics processing units. GPUs are what you use to run AIs. So they work better than CPUs, actually, just because of the way their architecture works. But you can see that in the last 2 generations, especially of GPUs, they're getting bigger, because to develop or to deliver the increase in performance that consumers are expecting from successive generations of GPUs, they've got to increase the size because they can't make the transistors smaller. So where do we go? Well, I think AI, you'll still get a lot of improvements in AI from functional improvements, right? You improve the network architecture, you learn about how to implement these AIs, they'll get better. Another prospect is quantum computing, which again is in its infancy, but there's been some research showing that for certain problems, quantum computing is actually going to be better than transistor-powered neural networks. One prospect is having actual physical neural networks. So no longer having neural networks simulated by transistors, but physical neural networks. What makes this possible is something called a memristor. I won't bore you with the details, but it allows a transistor to store memory. So a transistor will act differently based on how it was activated and what kind of current it had running through it last time. So that's a transistor that can store information. Transistors currently can't store information. You have to have separate computational memory units in your computer. This opens up the possibility for actual simulated physical neural networks. And my last prediction is that AI augmenting humans will be better than either on their own. And you see this repeatedly, right? We're in the early days of AI, but you see this all the time. So this is a guy, a Twitter account called Stealthy. So what he does is he does AI generated selfies throughout the ages. This is a made up person. This is not what the guy actually looks like. But each of these images, this is not just from an AI. Each image is usually a composition of like 5 different images. He blends them together. He has to do something called in painting to get his little stealthy dude in there. So this is a lot of work. He's a very talented graphic designer, and these pictures are super cool, and it's not something that an AI could have done on its own. And let's go back to Beethoven. So the guy on the top, these are two team members of the Beethoven X team. The guy on the top has a PhD in music theory from Harvard. The guy on the bottom is a music producer. They were curating the things that an AI was producing. That music clip you heard was not actually just generated by AI. It was generated by an AI and curated and arranged by two humans with a lot of experience in what makes good music. And so finally, I'll comment on surgery. So, you know, what will AI look like for surgery? Well, people always talk about autonomous surgery. This is where autonomous surgery is now. So this is the only autonomous surgery platform for abdominal surgery. So there are autonomous radiologic surgery platforms like Gamma Knife, and there's autonomous orthopedic surgery platforms, but nothing really for the abdominal, nothing for the gastrointestinal system except this. And this is an anastomosis model. So at this point, the AI-run robots can do an anastomosis that is as good, if not better, than a human doing the anastomosis. It takes 4 times as long. Okay, what does that actually look like? It looks like a surgeon doing the entire operation in dissection, arranging the pieces of bowel for the robot, the AI-powered robot, maintaining the bowel in that position for the duration of the anastomosis. You have to place near infrared markers on the bowel for the robot to look at because it has a lot of trouble distinguishing what it needs to sew without the near infrared markers. And then you have to first assist the robot and keep the suture out of its way. It's extremely cumbersome. And they've found that these AIs just really don't do well with biologic tissue. They have no mechanical sense, right? Like we saw with the box opening, it doesn't understand what tissue really is. And so I think we're really far from an AI that can actually understand tissue planes, understand that the human body is something you can disassemble and reassemble, and actually carry out a dissection. We're very, very far from that. Well, what will AI-assisted surgery look like? Because I think that AI-assisted surgery is where we're going and not AI surgery per se. It's probably going to look something like this. So this is a product out of France. Harvard also has something like this. And this is just an overlay for you to have during a laparoscopic cholecystectomy. It shows you safe and not safe, right? And the idea is that during a difficult cholecystectomy, you can flip this on and have an overlay and know what's safe and not safe, where you can dissect and where you can't, and hopefully decrease the risk of bile or reduce the risk of bile duct injury. So probably for us, you know, keep your day job, but expect to be an AI-assisted surgeon sometime in the future. And so, what have we talked about? Well, we've talked a lot about AI. I think I've made the argument that neural networks are statistical algorithms and not networks of neurons. I think I've talked, you know, that hopefully tried to convince some people that AIs are fundamentally different in structure and function from the neurons in your brain. We need to have problems that are translated easily into mathematical form, vectorizable problems. We need to have good, robust data, and we need to not expect too much from our models. We can't expect them to be human brains. We can expect them to be very good, revolutionary statistical algorithms, but we can't expect more. And the future of AI in surgery, I'd say, is likely AI augmentation, not AI automation. All right, I'll take any questions.
Thank you, Dr. Reed. Excellent, entertaining talk. Blade Runner is probably my favorite movie. Dr. Zoka here. So for you, you're doing a fellowship and then going out into the world. Will AI research or work will that be in your future?
I hope so. The thing about AI research is that it's much like implementing an AI. You really need a multidisciplinary team. You need machine learning engineers, statisticians, data engineers. You really need to be at an institution where that's feasible. And you have different people who are working on that, capable of working on it, want to work on it, and you have the database to work on it. So it would be very exciting to be a part of that. It's something that I'll probably, you know, keep the pulse on no matter where I end up.
And part 2, what do you think the most valuable AI tools will be? Kind of mentioned a few, but Like if you could make up anything for surgery, what's the most helpful thing?
I really don't know. The people that do, I mean, if the past 7 years, if the years since 2016 have shown us anything, it's that we don't really understand what we made. And so I guess I'm not really sure about, what's going to be most valuable in 10 years. I'd have to say that I don't know. The people who do this research think that it's the overlays. If you look at what they're working on at Harvard, it's event detection and overlays. So staying safe in the operating room, not necessarily operating itself, but monitoring the operating room, monitoring the operation, and making sure that the dissection and the surgery is safe.
I think based on what you've shown, at least for what we do, and I think we do tend to not overemphasize, but we emphasize the operating room. But and I would say this is one of the best talks I've ever seen, and I didn't understand how fundamentally it works, and I never will like you do, but I'm much better after this hour. And since it is all distributions and understanding, looking at the data, I think in surgery it'll be our decision. We'll have the highest risk, after Whipple when you operate for a preventive reason, right? For like adenomas with high-grade dysplasia that you would need them, like Mr. H, you've been taken care of for how many weeks now, right? So we did his operation as a preventive, but did he need it? Was he going to get cancer? Well, it sure would be nice if Sydney could have told us that or not, and told us when.
It would have been nice. She might have been a little crazy about it.
Yeah. Anyway, thank you. This was really good.
Oh yeah, Dr. Gross.
Yeah, that was your talk. That was awesome. Top notch.
Thank you.
I really appreciate it. What do you see the role of AI in education? I think, looking back on your years as a resident, how do you think AI is going to play a role? And then is education forum a way that we can train AI better so that we can then translate it into
So the question was, what is the role of AI in education? And that's actually a really exciting, to me personally, one of the more exciting aspects of AI in surgery. We've reached the point, there was just a paper published, I think in the Annals of Surgery, I think. So we've gotten to the point where, to get an AI to really understand an operation, I mean, it's just too much for an AI. A neural network would be drinking from the fire hose. So you have to do what you call segmentation. You have to break up the AI into, you have to break up the operation into discrete portions. And if you're asking the AI to evaluate technical skills, you even need to break up sometimes the technical skills into discrete things, like how do they load the needle? How do you respect the tissue? How do you hold the tissue? How do you pass the needle? Like an AI has to evaluate each sort of segment. It's called segmentation. You have to each thing by itself. We've reached the point where an AI can accurately segment operations and can evaluate, how good the surgeon is to a reasonable degree. And this paper is just published. I forget where it was from, but so they developed an AI that was able to segment. I think it was like nephrectomies. And accurately grade, like novice, intermediate, or expert. And then actually, there's something called, there's a movement called explainable AI, where, regression models are, again, I keep using this word, but parsimonious, where it's a nice, easily understandable model. And you can train your AI to spit out sort of like parsimonious output. So this AI also spit out things that would predict whether or not you're a good surgeon or a bad one. So they spat out like scores for individual components like tissue handling, needle loading, efficiency of movement, and that kind of stuff. So that's actually, as far as like mentorship and improvement and lifelong learning, I think that's going to be huge. Is the ability to sit down at a robot or even operate laparoscopically and have an AI point out things that you can do better. All right, thanks. Oh, okay. Mm-hmm. So let's go back here. So the Harvard model looks a lot like this one. This one's from EarCAD, which is like a French minimally invasive surgery institute. But the Harvard model does the same thing. So what you do is you train it on images of the critical view of safety, and you train it on images of gallbladders, or you like give it images of a gallbladder, and you ask a bunch of surgeons to point out on that picture where they think it's safe to dissect and where they don't. And then the AI learns that. And so the AI will put an overlay, like a little, like this, of like, so it'll segment each area of the picture into safe and not safe, and then it'll display that segmented overlay. Well, we're doing that already. So that's how they designed the STAR robot. So the STAR robot does have to account for tissue deformation during the anastomosis. And the data they're feeding it are good data. And the network architecture is robust, right? I mean, I think he's at like NYU or Cornell or something. And these are world-class machine learning engineers that are dealing with these problems. So I think the problem is in the AI architecture, and just the fact that we're using basically an AI that recognizes image distributions and expecting it to have a mechanical sense of what the world is like. And I think it's just unrealistic. I don't know particularly. I know that there are one of the automated like AI surgery models that I've seen is one that can navigate blood vessels, like autonomously navigates blood vessels and tries to get something into the heart. I don't know how flow plays a part in that. All right, thanks much. I pressed the button to stop recording. Just closing down.